It's great to see so many people here. Wonderful to be back in London and in this great venue. So I'm going to talk about binary compatibility, which is not a topic to rejoice, but it's rather a topic to wear the hair shirt and repent and say, oh my God, binary compatibility, that's really terrible. Have we been too undisciplined? Change things all the time, break users' code. So I'm going to talk about that, and I'm going to argue that it's, in some sense, a problem that is actually not solvable with the technology that we have, and that we need new technology to solve that problem. So what is the problem? So in a nutshell, it is that where the issue is you either can break your client's builds or you can stop to innovate. So it's been, as I said, an issue ever since Scala became popular. Causes grief when building. So essentially you have a library, you upgrade to the next version of Scala or another base library like Akka or Play, and your code breaks. And that's, of course, a very frustrating experience that you say, well, it doesn't build anymore. Why does it not build anymore? Who caused it not to build? We have learned to deal with it bit by, in a nutshell, becoming more conservative. So that means changing things less often, having longer intervals for changing things. But that's also good things like bug fixes or improvements, optimizations that now have to wait much, much longer before they can get in there. So the conundrum is, well, we can either go loose and fast and break clients' builds all the time, or we can go really slow or freeze and stop improving. Is there no third way, really? Do we have to choose between the two? Well, before I go into the proposed solution, let's have a look at what is binary compatibility, because it's sort of this thing which is people don't like to think about. They just like to, well, when it happens, it's like a thunder striking, and you just curse the computer, but it's not something you want to actually actively think about. So there's a difference between source and binary incompatibility. So this one here exhibits both. So you have an object client, and it calls message.length, and message is defined by a string ABC in the server. And now you change your mind in the server and say, well, my message should actually be an option of a string. So you change it like that, and then, of course, the two things won't work anymore together. And they won't work anymore in binary. That means if you just load the jars and run them together, there will be a conflict, a linkage error. And they won't work either in source. So if you try to recompile this client, then you would get an error, of course. You would say, well, you can't take the length of an option value. So here's another incompatibility, which actually is still source incompatible, but binary compatible. So you have an object client, and it imports A and B, two server objects on the server. And it says, again, x string equals 1. And then on the server objects, you have the first one contains an implicit conversion from int to string. So that's why this line works. So that implicit conversion is called here. And now in your evolution of your library, you say, well, my implicit conversions from int to string, they are so cool. Let's invent a second one and have one here. Now, if you recompile this object, you would get an ambiguous implicit. It would say, well, I don't know when I go from an int to a string, I don't know whether I should use this one or that one, so you get a compile time error. But binary, everything is OK, because binary, in the bytecode, we actually already have picked our implicit. There's a hard-coded call to the F in here, which will survive this change, of course. So that's not a problem. But the big problem then is the other way around. Something that is source compatible and binary incompatible. So that's a very simple example here. You have a trait edible, and a thing that's edibles has joules, which is a double, and then you have an apple, and it has 500,000 joules. Amazing, but it's true. So now you want to go and evolve your library. It says, well, it's actually convenient to have a method calories, which is joules times 4.184. Now what happens is if you run this code with that library, then you get a binary incompatibility. It's source compatible. This thing will compile just fine. It it doesn't even call calories, but even if it called calories, it would compile fine. But the binary compatibility persists. So why do we have a binary incompatibility? So let's have a look what the compiler actually does with these traits and the client objects. So what it does is, since traits are not in Java, it converts the traits to an interface. So here you have the interface edible. It has joules and calories as double methods. And then the implementation of calories must be somewhere, can't be in the interface. So we put it in essentially as a companion object, which is called edible $class. And that calories contains this very complex computation. And it does the computation on essentially an object that we pass. So that object is called $this. OK, so what about the client then? So here's the client. So here's what the compiler has to do with Apple. It has to, of course, insert the code that's there. And then it inserts another method, which calls calories. Essentially, the calories method on Apple is just a forwarder to the static method or to the object method calories here. So that's what it does here, edible class calories. So you can't inline the code here, because typically with separate compilation, the compiler doesn't know what's in the body. It only has the name of the method, and it says, well, the convention is if there is a non-abstract, a concrete method in a trait, then there will be the same method in this companion class, and it will be static, and it will have a $this parameter, and therefore we can call it and thereby get the implementation of this method. But now the problem, of course, is the first version of Apple against the original library. There was no calories, so this whole thing is missing. So what we would get if we run the first version of Apple with that interface, we would get an abstract method error, because calories, the first version of Apple did not implement calories. And that's something that is an error. The VM will refuse to load your program. Whereas at compile time, of course, everything is correct. So it's a binary compatibility error. Now, that thing actually got fixed in Java 8. That's a so-called default method problem. So you can have default methods in traits. So in this concrete example, it wouldn't be a problem. But you go one tiny step further. For instance, you want to add a method that overrides some other method in a trait or a class. Then essentially the default methods can't resolve the thing anymore, and you're back to square one. So essentially default methods, unfortunately, they help only a tiny delta. They don't solve the problem. They give you just suppress some binary incompatibilities and leave many others. Another problem that default methods don't solve is any form of fields in traits. Again, these fields in traits have to be implemented in the implementing class, and that even persists in Java 8. So you might say, OK, annoying, but now scale this up to a million-line system. In a million-line system, you will basically, the fact is that anything that might go wrong will go wrong, right? Somebody will have written code that will exercise any anomaly there is. So that means in a million-line system, you sure are going to hit many of these problems, and they will block you to progress. There's another issue which I've come to realize only over time, and that binary compatibility issue is actually not in the user code, but in the compiler itself. So in the compiler itself, you have lots of things over the years. I mean, compiler is now almost 7 years old, where you want to fix things, where you say, well, something wasn't ideal initially, we want to fix things, but the fix would again affect the compilation scheme and therefore break binary compatibility. So one example here is lazy values. So here I have again my edible thing, but now I say, well, I want to have an optimization. My calories computation should be done only once. So I don't want to recompute this multiplication every time. So that's why I make it a lazy value instead of a def. Now, if you look at the implementation of that, so that is slightly simplified. That's not the real one. The real one is more complex. But the essence of it is that we would need for that a bit set in Apple, which essentially contains for every lazy val that we have a bit, whether the lazy val is initialized or not. And then we would also, for the lazy val, of course, have a variable that contains the eventual value of the lazy vals. And then the getter, so the actual method that accesses it, would check our bit set. And if the value is not yet computed, it would essentially call another method that has to be synthesized init calories to compute the first value, and it would store that in the field, and it would set the flag to true to say, well, now I have the value, so the next time around I call this calories, then I can return the value straight away without doing the computation. Okay, now, so good, so far so good. The problem is that so far, in the current implementation of Scala, we still spend 1 bit per lazy value, which means now that if we want to put this whole thing into a multi-threaded context, so here I've given you only the single-threaded context, so this thing is not thread safe, but the actual lazy values is thread safe. So what I would need to do is there's some locking in here, and essentially while I do this initialization call, while the initializer is computed, the object stays locked. That's the bit what it does. The problem is that if during the computation you come back to the original object and want to access it, then the object is locked, and another thread cannot do that. So there's a nice talk by Daniel Spivak, I think, that explains why this is a big problem, why you can have actually code that would deadlock because of lazy vals. So there is a scheme to change that, and that scheme would use 2 bits instead of 1 bit per lazy val. Essentially what you do is you have a very short section where you lock and you say, okay, you have 1 bit to say this lazy val is now in train to be initialized. And now if another process comes and wants to access the same lazy val, it goes again through a very short critical section and says, well, if it's currently initialized, then mark it as initialized and contended, and I put myself in a queue. And then when you come back and with the final value of the computation, you say, well, if it's contended, then notify everyone who would wait for this object. So now you replace 1 long critical region that can deadlock by 2 tiny ones that cannot deadlock because nothing ever can happen during these critical regions. Net win, but of course when we do that, all the bits will shift in all the lazy vals anyone has ever written. And that means, of course, it would be binary incompatibility. So you can't just roll in this fix as a clear improvement at any point. You have to wait for essentially a big change the world event. So if I look at the current compiler pipeline, and we'll see more of that in the future, so that's essentially, again, a slightly idealized version of actually the new Scala compiler. So that's all the phases there are. There are more phases in between. There's a lot of things that happen, from type checking to finally when we spit out JVM bytecode. And all of these phases, each one of them makes a decision of representation, essentially. How do I represent something? How do I map something? And each of these decisions can affect binary compatibility. And even though we strive to get it mostly right from the beginning, nobody gets everything right from the start all the time. Or rather, I guess things change. And that means that we are, again, essentially tied down from from improving and fixing bugs and maybe also optimizations. Okay, so just to go back and say, well, what is actually the symptom of a binary compatibility fault? So what you have is you have a client A and a library class C, and you do a binary incompatible source change, like add a new method to a trait or add a field to a trait, or change your compiler to use 2 bits for a lazy val. So that gives you a different class. But then if you compile the new, if you run the first previous class A and the newly compiled class C, you will get a binary incompatibility at runtime. Why is this such a big problem? I mean, okay, we know the problem now, we realize the problem. Why is this such an enormous problem that essentially holds us down? Well, here's sort of a very typical and very bad scenario. So you have the Scala library, let's say it's 2.10, and then you have just your business grows, you have a large deployment of Scala in your company, and in some corner, there's this dusty legacy library. The developers have long gone. Nobody knows how to compile this. Nobody even knows how to build this thing anymore. And unfortunately, your application, your shiny new application that, of course, is perfectly well maintained, relies on this dusty legacy library in some way. Okay, so now Scala comes along. We have a new shiny library, 2.11, and let's say, I'm not actually sure that's the case, there was a binary incompatible source change in CQ.Scala. I'm sure there were many, but I'm not sure one was in CQ or elsewhere, but it doesn't matter for the argument. Okay, so the dusty legacy library can't be rebuilt because nobody knows this thing anymore, and maybe it even needs to be upgraded because it uses implicits in interesting ways and the implicit resolution has changed or whatever. So it might require a little bit of work to build, as these things sometimes do. So can't be bothered, you can't rebuild. But now it means that your shiny new application is stopped from upgrading as well. Because, it can't use both the new library and the old legacy lib, because that one needs 2.10 and the new one needs 2.11. And that's a problem that is very, very common, and that's why binary compatibility is such a huge problem. And I should say, it's actually not just Scala. Scala just was first because it was sort of the first thing that was used a lot. It applies to any sort of basic library out there. So you could very well have a situation where, let's say, your library relies on some version of Akka, and you upgrade Akka in a binary incompatible way, and you have exactly the same problem. Or you could have exactly the same problem with shapeless. If your library relies on shapeless in something and you upgrade it in binary incompatible ways, then things will break. Okay, so what do we do about it so far? So we have actually done quite a lot. So the first thing about binary compatibility that you can do is you can try to detect it. So that's a must, because otherwise you're flying blind. And there is a tool, it's called MIMA for Migration Manager, that can detect binary incompatibilities. So you give it two versions of a library, and if the new one is binary incompatible to the old one, it will tell you, and it will tell you where it's binary incompatible. And the second element for a solution is that we have become much more conservative in the release policy. So for several versions now already, the minor versions of Scala must be binary forwards and backwards compatibility, compatible with each other. And that's checked with this MIMA tool. So that means backwards and forwards, that essentially any minor version is a drop-in for any other, backwards or forwards. It shouldn't matter at all for building. And this is, of course, very good, but it's also super, super, super constraining for what kind of bugs we can fix when. Major versions are still allowed to break binary compatibility. There must be sort of a pressure valve that at some point you can do meaningful changes, but they're released rather rarely, and the release cadence is going down. So I think right now we have sort of something like 18 months between them, and it's growing. The problem with that is it's only a partial solution, because this policy only so far affects the Scala library, but like I said, third-party libraries need similar policies, but often don't enforce them. And the second big problem is that innovation is stifled. So simple fixes have to wait for a long time to get in. And furthermore, what I see in the Scala team, lots and lots of development cycles and brain power is spent on dealing with binary compatibility. So it's not good enough to just say, well, I have this problem, I have this fix, but now you have to study, well, in what way does it affect binary compatibility? What kind of migration policy could we do? And that sort of becomes an increasingly large part of the total engineering effort. So it's not so easy. It seems not just a lack of discipline, but a genuine problem which doesn't have a simple solution. Well, maybe we should look what do the others do. So because it seems that this problem is more pronounced for Scala than in any other community. You could argue it's actually a Scala-specific problem. So what does Java do? Well, in Java, actually, the language is very close to the JVM bytecode. The compiler, translation from the compiler to the bytecode is pretty clear and pretty standard, not much happening there. And what is in innovation mostly happens at the JVM level. So I mentioned, for instance, traits and methods in traits. In Java, they could have done the same thing, but they would have gotten the same binary compatibility problem. So what they did instead is default methods, and default methods is a JVM abstraction. If you have the JVM, you can do lots of very cool stuff that you can't do otherwise. So Java actually has this possibility to work on the JVM, and that helps them a lot. The other policy in Java is that essentially over the time there have been just very rigid practices that help binary compatibility. So the first practice is never throw away a library. That's why we still live with Java util date, even though everyone knows it's broken, but you can't change it. And the second one is, at least previously in some frameworks like Eclipse, what you did is if you wanted to add more methods to an interface, because that requires recompilation of every implementation of the interface. They didn't do that. Instead, they essentially had version numbers on interfaces. And then client code had to say, well, if this is interface 4, then I can use this method. But if it's just interface 3 that I get, I have to do this workaround. And Erich Gamma, the essentially head, who was the head of the Eclipse project, would stand here and say, this is a feature. This is great. This is how you have to do it. Okay, the other thing that's interesting is, because it's a completely different solution, is OSGI, which allows multiple versions of a library in an application provided they're in different OSGI containers. So here, presumably, what you could imagine is that you have this situation as before. My application, Dusty Legacy Library, Scala Library 210. You upgrade to 211. And now, essentially, you just rebuild my application, and it would refer to this and this. But if they're in different containers, then actually the Dusty Legacy Library could still continue to use 210, whereas your application uses 211. In principle, that can be made to work, but it's very fragile. It requires serious class loader magic. And in the end, very few frameworks beyond Eclipse have bought in. So that's, I believe, also not a solution that we can use universally. How about C, C++? Well, they have a linker, and that gives you a lot of flexibility to actually paper over differences in the interfaces. And overall, it has to be said, it's not that great a story either. So the name C, DLL hell didn't come in vain. Closure doesn't seem to have a problem with binary compatibility. No, they don't, because they built from source. So that's a nice thing to do. JavaScript also builds from source. Python builds from source. Ruby, Go, they all built from source. So it seems a lot of the languages that don't have a binary compatibility problem don't have one because they're built from source. So why can't Scala do that? Why can't Scala build from source? Well, there are a couple of problems. The first problem is there's no standard build tool. So we have a lot of build tools in the community. There's SBT, there's Gradle, there's Maven, Plain Ant, Ivy, and people use different things. So you can't just by fiat standardize on a single build tool. And the other thing that happens is that to tell the truth, reproducible builds, so essentially reliable builds that you can put in a system and this component will just build. In Scala, they're actually quite rare. So it's not common at all to have that because it's not needed. You have the binaries. So people build from binaries so they don't need to invest the effort to get to producible builds. And in a sense, that's a chicken and egg problem. So because everybody is used to binary builds, nobody invests in making the builds reproducible. Nobody? Well, that's actually not quite true. TypeSafe has invested a lot of effort in the community build, and they can now build more than 1 million lines of community projects every night with the new versions of the Scala compiler, which is great. But it was also a huge effort, essentially 2 persons working for more than a year, I think, on this thing. So it just shows you that it's a really hard problem in Scala land to get reproducible builds. And while we should get them and we should work very hard to get them, I don't think that's essentially a solution that we can adopt everywhere and every time. So I think what we need is a sort of declaration of independence, an interchange format that captures the essence of Scala dependencies and not JVM bytecode dependencies. And it can't be source either because source is essentially too fickle. So the idea that I want to propose and where I would be happy to discuss with people and get your opinions on that is to use type trees as an interchange format. And I'll argue that type trees are much more robust than source. They're much more stable than JVM bytecode. And the question that we have to answer is whether they are efficient enough. So let me let me explain what I mean by that. So the idea now would be to split the compiler pipeline in essentially two tools, the front end and the back end. So the front end would essentially contain the parser, the typer, then some small phases that just essentially normalize things, adding synthetic methods and stuff. And then it would spit out these typed trees. And the typed trees would then be the input for the compiler backend, which is essentially all the other phases until the last one, which is gen bytecode, where you would spit out the bytecode. There would be a sort of a direct path in the tool where you could say, well, let's go from here to here directly, and thereby essentially still have a compiler that spits out bytecode as before without doing the detour of typed trees. But even if you spit out bytecode, essentially the typed trees would be added to the bytecode as an annotation. The same way we now add essentially the Scala-specific symbol information that gets added to the bytecode as an annotation. And now this thing just would be much bigger. It would contain the whole tree of the thing. So then how would we build? So here we have essentially three artifacts, C, B, and A. And essentially in the bytecode, I have the tree as an annotation, and I have a hash, which essentially says, well, what is in this thing, and what does it depend on? I hash over everything. So now if I go to a new one, new version of class C, with a source change, I recompile, so I get a new version of the class, of the tree and the hash, represented here with a slightly different color. And let's say I want to, in my build, I say I want to build an A. So the A up here is my build. I give that command to the build tool. So the build tool would actually look at my dependencies and says, I actually risk a binary incompatible change here because this hash requires essentially a C with hash 1, hash C1, and I have a new hash. So there has been a change. Better be sure and recompile. So the first thing the build tool would do is it would recompile the B class, but it would do that from the tree, from the type tree, not from the source. It doesn't necessarily have the source. So it would rebuild from the tree. And once it has that, it can rebuild the class A again from the tree. So why is this better than source? This looks very much like our incremental mode in SPT now, so that the incremental node does very much the same thing. But of course, the incremental node in SPT works from source. Why is this more robust than source? Well, if you look at the front end, then there's this phase typer, which actually does a lot of different things. So it resolves names. That means it has to scan packages, handle imports, establish implicit scopes, overloading resolution, so find the right version of an overloaded methods, implicit search, conversions, apply conversions, such as eta conversion and the others, infer type parameters, assign types to trees. That's a lot of work. So it's overall, the whole thing is in the new compiler 5,374 lines currently, and a lot of things can go wrong there. So what can go wrong there, for instance, is the source incompatible change. You saw somebody plops a new implicit somewhere, and implicit search goes wrong suddenly because now the implicit is ambiguous. These are the sort of fragilities that can go wrong in this phase here. And type trees don't need to do them because they work afterwards. So all this has been done, and our format is already normalized. So we don't need to do this anymore. So all we need to do here then is to say when we convert these trees, transform these trees, there's a very, very small module called type assigner. And that's the module that essentially just fills in the type of a new tree that we construct. And we actually were able to split out the type assigner from the main typer, which was like 5,300 lines, into a thing which is just 311 lines. So there's a much more chance that we can actually trust that this thing does the right thing. So that's essentially the technology that would help us do that. It's much more resilient than bytecode because we can now add fields and methods to traits, add lazy vowels anywhere, change compilation scheme in any way necessary. And none of these would be binary compatible so far, but now they are. Because all of these things happen in here. And if something happens in here, well, that's just generating the bytecode. If the compiler changes, then, well, that would be reflected in the hash of things, and then you would just recompile everything with a new compiler. And we can also, of course, add and remove implicits, add methods anywhere, and change imports. And all of these could be source incompatible. So all of these would be the sort of things that would be fragile building from source, but we don't care anymore. We have already resolved implicits. We have resolved imports. We know exactly what we want to get to. So in a sense, this is exactly the same thing, or philosophically the same thing as Java bytecode, only on the format of Scala, so that we now see, well, what are the true Scala dependencies, and not sort of the artificial things that we compile down into Java bytecode. Is it efficient? Well, there could be some issues, because after all, these type trees transformers will be pretty heavily used. You could have a system of 1 million lines or more. So the possible issues is, well, how big will these trees actually become on disk and in memory? And how long would it take to actually compile these things to bytecode? So tree size is a potential issue. So here's just, I amused myself to do just one example here. That's my source program, 17 characters, xs.filter greater 0. And that's the tree that results. So here I counted 16 nodes, not counting the types. So these are still untyped trees, so there are no types in the trees. If you want to count the types, it's even bigger. So if we want to do a back-of-the-envelope calculation, so 16 nodes on the Java VM, maybe the average size of the node is 32 bytes. So it gives us 512 bytes. To double the type info, let's be optimistic and say it's only a factor of 2. Might actually be more to add the type info to that. So that means we go from 16 bytes to 1 kilobyte tree, factor 64 blow up. And that means if you have a 1 million line system of maybe 30 megabytes source, then you get 2 gigabytes of the trees. That's pretty substantial. 2 gigabytes to store it, to transform it, it's a heavy thing. Fortunately, of course, there's a much more compact representation. So the representation is not yet cast in stone. So this is just one idea how to do it. The idea would be to say, let's represent the tree essentially as a traversal, as a prefix traversal of the tree. And let's apply the same techniques that we use essentially to make the symbol information very compact, so essentially length dependent. So essentially we have numbers that are only as large as needed. So up to 128 you use 1 byte, then up to 16K you use 2 bytes, and so on. So you have 7 bits of payload and 1 stop bit. And these sort of things that give you much better compression factors. So that would be the same tree with the compression factor. And here what we've done is we actually have, for every internal node, we have actually added the size of the subtree of the node. And I would actually propose to add that in the binary tree directly, because I think one important thing for the binary trees is that you don't have to expand them all into actual Java objects. Generating 2 gigabytes heap from 0 to something requires a lot of time. Whereas often we don't actually need to do that. We can just take essentially these trees and explore them as far as we need to. So if you have essentially these skip distances, then it's very easy to navigate in a tree, even in a compact tree, because we can essentially just, if we have a tree index, just say, well, how big is this tree? So should we look at the children of this tree or skip on to the next one? So this is still navigable. The types and the symbols are given at the leaves. So here, essentially, what I have done in a type, for simplicity, I've written this with integers. So essentially, what this select term with sig says, well, I have an identifier, it's called XS, and I select the filter method. And because there might be several filters, I have to actually also tell you what the type of this filter is. So the erase type is function1 to Boolean. Oops, there's a 1 O too many. In the actual implementation, there would essentially be pointers to a type or symbol structure that would tell you what this thing is. What's important is that the types only need to be given at the leaves. So essentially, when I have identifiers or select nodes or definitions, in all the interior nodes like apply or closure, they don't need the types because our type assigner can recompute them reliably and very quickly. So that's the other thing, the other big win, that even if we want to keep type info in the trees, we only have to keep it at the leaves. Speed, so if we look at currently what the system is, so transformation and bytecode generation amounts to about 60% of total compile time, which is fairly large, but there are a number of techniques we can use to speed this up, and we are already using them. So we can fuse the phases, so reducing the amount of intermediate trees. So a lot of these phases actually are run essentially together, and they don't produce intermediate trees, but they immediately are applied to the trees produced by the previous phase. The type assigner is much faster than the typer because it has to do much less. And there's a lot of scope for parallelism as well. We can use it to build different files in parallel. And besides, of course, all this thing is incremental. You have to do it only once when a library changes, so hopefully not that often. So I think that's actually quite manageable. Binary compatibility is one advantage of the scheme, but there are other benefits, quite significant ones, I would say. The first is optimization. So type trees are a great format for interprocedural analysis. That's precisely what you want to do that. They're great for inlining. So on this level, it's very easy to actually inline code. And you can do inline without regrets. So inline now, while we could do it, always has this problem of binary compatibility. You inline an implementation. What if the implementation contains a bug? Somebody else does the bug fix in the original library. If you don't recompile, you still have the buggy thing in your code. So you don't profit from updates. Whereas here, that's not true. Since binary type trees are the interchange format, we actually immediately profit from all the optimizations anybody does there. Program analysis, I think they're probably the ideal format for program analysis because they are easy to traverse and rather minimal in the sense that there are not many rules. It's easy to digest, but they're still very close to source. So if you want program analysis that actually afterwards makes sense on the source level as an output, so something like find bugs or things like that, then I believe that's a great format, also for instrumentation. And finally, the idea of these type trees are that they also will make it very easy to target different backends as long as the dependencies exist. You could have a library that's used in the same way on JVM, JavaScript, LLVM, whatever backend we have, and it wouldn't need explicit recompilation. So the library would just, you could drop the library and, well, there would be for every backend, there would be a different compilation pipeline, which is mostly the one you've seen, only at the end it differs. And again, it would be completely transparent how you compile this library to the new backend. Of course, only as long as this library doesn't use any platform-specific things. So I would imagine that something like Scala C or Shapeless is very portable, but something like an I/O library is not. And finally, the idea here for the portability is also that I think it could be a great format to essentially bring back the new compiler we're working on and the old Scala C one, because what we would do is we would have the old Scala C compiler here that you see in red. We would have the new front end, and both of them would essentially, for the Scala C, optionally produce these type trees. And then the type trees could take over, and actually at the end it's the same Gen B code. That's Miguel Garcia's original module that's now going to be used in Scala 2.12 as well. So Gen B code we will standardize on the actual bytecode emission. But here we would actually have the old backend, which probably nobody should touch anymore, and the new backend, which would take these type trees, and Scala C could directly profit from that by generating them, and thereby would immediately profit from the binary compatibility and maybe in the future from the optimizations as well. So to conclude, I think type trees can fix the binary compatibility problem, and they have lots of other benefits as well. So let's get started to make them real. Thank you.